Hello everyone, my name is Fernando Pereira, and today I will talk about our paper, a comparative study on the accuracy and the speed of static and dynamic program classifiers. This is a work that I did with my colleagues Anderson Faustino from the State University of Maringá in Brazil and Geronimo Castrillon from the Technical University of Dresden in Germany. The goal of this project is to evaluate program classifiers, which are tools that take in a program and then determine which task the program solves. Program classification is useful because that's a building block of many applications, mostly in software security. So program classification is at the center of tasks such as malware identification, plagiarism detection, redundancy elimination, and code lifting, to name a few. And in this study that we carry out in this paper, we evaluate three different approaches for program classification, which we call static, dynamic, and hybrid. These approaches differ on their ability to observe the execution of the program. Something that will be important in this study is that we use the same program representation to evaluate the different classifiers. So essentially, we are answering the following question. If I can execute the program, can we do better classification than if I just look into the static view of the program? And by program representation, I mean histograms of instructions. So we shall extract histograms of instructions either from the program execution or from a static image of the program. So let's understand what a program classifier is. Given a program P, the job of the classifier is to determine which problem P solves. In other words, which task is meant to be solved by the implementation of P. And in this sense, we can train the classifier showing to it several solutions to several different problems, pretty much like we train image classifiers. In this paper, we use programming marathon problems to evaluate the classifiers. Let me show you an example of a typical problem here. So given a positive integer n, what's the sum of the digits of n? A problem usually specifies constraints on the inputs. For instance, n must be an integer between 1 and 10 to the nth. And then it specifies how the output must be produced. I mean, the problem describes the syntax that must be used by a solution to the problem, to the program that brings that solution. And then we typically have examples of inputs and outputs. As in this example here, for the input 1, 2, 3, we want the output 6. Then to run a trained classifier, we convert a program to the representation that the classifier accepts. This representation is usually a vector. In this paper, we use histograms of opcodes. We call these vectors program embeddings. They work as inputs to the classifier. The classifier is some machine learning model. In this paper, we shall be using mostly random forests. We pass the embedding to the model and ask to that model which problem that embedding is meant to solve. The classifier already knows a number of problems because it was trained before, and then it chooses among the problems that it knows the one that's the most likely to be solved by that embedding. Again, in this paper we shall be experimenting mostly with random forests, but the actual model is not important. We could use anything, linear model, multi-layer neural network, anything. And as I mentioned in the beginning of the presentation, we shall evaluate three classification paradigms. The static classifier does not run the program. It can observe a static image of the program only. For instance, it can observe the x86 image of the object file. From this image, it computes a histogram of x86 instructions, which will be our embedding. Or else the classifier can use the LVM intermediate representation of the program, for instance. And like before, it counts the number of occurrences of each instruction and builds up the histogram of instructions in this way. A dynamic classifier, in turn, can observe the execution of the program. So it depends on having access to the executable binary and also to the inputs of that program. It observes the sequence of statements that run during the execution of the program. So it has access to a dynamic view of this program. In this paper, our dynamic view is the stream of x86 instructions fetched during program execution. From this stream, we build a histogram of x86 instructions. As an example, the IMO instruction was fetched twice, so it contributes 2 to the histogram. A hybrid classifier is similar to the dynamic, but it does not count number of fetches. It counts occurrences of instructions in the dynamic slice of the executed program. So in this example, even though IMO was fetched twice, it's the same IMO, thus it counts only once. So again, in a hybrid classifier, each different instruction that is executed adds 1 to the histogram. But if the same instruction is executed multiple times, it counts only once. Notice that the difference between dynamic and hybrid classifiers is subtle. If each instruction in a program runs only once, as if the program does not contain any loop, then these classifiers will have access to the same embedding. But if some instruction runs multiple times, then the dynamic classifier will count more instructions than the hybrid classifier. For instance, imagine a given IMO instruction is fetched twice during the execution of the program, as if it were within a loop, for instance, that iterates twice. Then the dynamic classifier will see 2 in the histogram for IMO. But if that's 2 executions of the same instruction, then the hybrid classifier will only count this instance of IMO once. Now, you might wonder how we implement classifiers and how we test them. We do all that using what we call the Rochinol infrastructure. Rochinol is Nightingale in Portuguese. It is an open source repository that you can use to reproduce our experiments. You can extract histograms of the execution of x86 in ARM programs, or you can extract them from the image of these executables or from the LVM representation of the programs. Rochinol also includes a large dataset of programs and problems that you can use to train and test classifiers. And then there is all the infrastructure to set up games using classifiers and evaders to see how well the classifiers do, even when you try to obfuscate the program. These games are indeed a big part of Rochinol. That's a concept we borrowed from another paper that designed this methodology to measure the effectiveness of binary thieving tools that was published in CGO in 2023. The classifier can be trained with problems and several solutions to these problems. The evader provides the classifier with a challenge, which is a program in a class of problems, and then the classifier must try to guess which problem the program solves. So, in its most basic form, we have game 0. In setup, the evader simply gives a program to the classifier without doing anything with the program. That's a symmetric game. There are 3 more games, but of interest to us is just game 1 now. In this game, the evader is allowed to obfuscate the program before challenging the classifier with it. The obfuscator in this case is the adversary of the classifier. So in Rochinol, we can build classifiers in different ways, but regardless of the classifier, it all starts with a program. If we give the classifier a static view of the LVMIR, then we have a static classifier based on histograms of LVM instructions. If we give it a static image of the program's executable, then we have also a static classifier, except that it uses histograms of x86 instructions this time. If we give the classifier a view of the dynamic CFG of the program, then we have a hybrid classifier. It sees a kind of slice of the program that actually runs. And if we let the classifier count how often each instruction runs, then we have a purely dynamic classifier. To build this dynamic slice of the program's executable with instruction frequencies, we use CFG-grind. This is a Valgrind plugin. It's an open source tool that's fairly easy to use. If we build the dynamic CFG, it will build the dynamic CFG gradually, meaning that if we execute the program more than once with different inputs, then it can keep increasing the CFG as we see more of it. And it can distinguish instructions that belong to the program from the instructions that come from libraries, for instance, which exist outside the text segment of the executable. For the datasets, we take programs from online programming judges. In particular, we took the dataset that we use in this paper from CodeNet, which is a large repository of programming problems. We built an arena with 700 problems, each with 500 solutions. We made sure that each program that can be compiled with Clang and obfuscated with OLVM. And they have at least one input for which execution ends with status 0. That's to say that the program runs up to normal termination. Our obfuscator of choice is OLVM. It's an open source tool. It provides us with 3 obfuscation algorithms, which are instruction substitution, bogus control flow, and control flow flattening. OLVM is pretty effective. For instance, control flow flattening will convert a program to a huge switch within a while. We also use the different optimization levels as obfuscation algorithms. Optimizations can be very effective to change the syntax of programs, as it was demonstrated by Ran et al. In 2021. With this framework, we can address several research questions. For instance, what's the accuracy of the classifiers evaluated in this paper compared to either trivial classifiers or state-of-the-art binary thieving tools? Let me answer this question by comparing the accuracy of these tools. Accuracy is the number of hits divided by the number of challenges. So 1 means a perfect game for the classifier. For the trivial embeddings, we simply count instructions. A static trivial classifier can only see the size of the LVMIR of programs, number of instructions. The hybrid classifiers can see the number of different x86 instructions that were fetched. And the dynamic classifier can see the total number of instructions that were fetched during execution. Notice that for every classifier, we can vary the optimization level that we use to compile the programs. That's just to check the behavior of the classifiers with and without optimizations. As for the state-of-the-art techniques, we compare our classifiers with IR2VEC and ProgramL, which are program embeddings designed for tasks similar to those that we evaluate in this paper. Notice that these classifiers are purely static, for they do not really run the program. They use the LVM representation of the program to come up with an embedding. In this comparison, we shall consider 32 problems, each with 500 samples. We use 400 samples to train the classifiers and then challenge it with 100 samples. So if we challenge a random classifier, this random classifier has 3% of chance of guessing the correct problem that the program solves. So let's see. Our trivial classifiers have very low precision, still better than random, but only marginally better. It never goes above 12%. Then the state-of-the-art classifiers have pretty high precision, all above 90%. And here's the classifiers that we evaluate in this paper. They are more or less on pair with the state-of-the-art approaches. The purely dynamic classifier, in particular, almost never misses a guess. That's to say that using histograms of instructions as program embeddings is not a bad idea, but this has been shown in previous work. So let's compare these classifiers. In this comparison, let's try to vary the optimization level that we use to obtain the binaries that we compare. The setting this time involves 100 classes of problems, thus the random classifier has 1% of chance of guessing correctly. And we have our 4 classification paradigms, each trained and tested with programs compiled at different optimization levels. So as we see, the accuracy of the static classifier based on LVM instructions is about 95%. It improves a bit once we optimize programs. Something important, in this experiment, regardless of the classifier, mind that the classifier is trained and tested with programs compiled using the same parameters. That's not an adversarial game. So using x86 instructions, precision of the static classifier is pretty much independent from the optimization level, about 94%. With the hybrid classifier, precision increases a bit. Notice that it increases with the optimization level. Here we are actually running the programs. With the dynamic classifier, we obtain even better precision, and again, it improves with the optimization level. Indeed, in our observations, it seems that if we are allowed to run the program and observe this execution, the more optimized the program is, the better the precision of the classifier. Now, what if we have an adversary that's obfuscating the programs before it challenges the classifier? What happens in this case? Again, we can measure accuracy as the number of correct guesses over the total number of guesses. And we can consider all the three different obfuscation techniques we have, including the combination of all of them. In this experiment, we consider three classifiers: the LVM static, the x86 hybrid, and the x86 dynamic. We remove x86 static just to make the presentation shorter. So here we have the LVM static classifier, challenged with four different obfuscation techniques. Here the hybrid classifier, and finally the purely dynamic classifier, again challenged with the different obfuscation techniques that we have. And here we have the results. Precision drops considerably compared to the previous game 0, where there was no obfuscation. Before, our classifiers have precision close to 1. Now, if we use all the classifiers, in our best scenario, it never goes above 35%. And notice that it improves as we move from static to dynamic. That happens in almost every obfuscation scenario. That's more or less natural. The dynamic classifier can avoid that code, which is something that the obfuscators usually insert in the program. The only exception is flattening. In this case, the static classifier was the best we had. Apparently, the extra branches hurt execution more. Something you might ask is, what if the classifier can also be trained with obfuscated programs? Well, in this case, it recovers back some of the lost precision. And the same pattern happens. The dynamic classifier improves upon the hybrid, which improves on the static. What about the time to run classification? To answer this question, we can look into how long it takes to carry out static, hybrid, and dynamic classification using the different paradigms we have in this paper. So, in the case of the LVM static classifier, all that we need to do is to extract the LVMIR of programs. There is no need to generate an assembly file, much less to run it. Using the x86 static classifier, we must produce an assembly and analyze it. We do it using Capstone, so there is a small overhead to build the histograms. In the case of the hybrid and dynamic classifier, however, we must run the program, and mind it that we are running the program through Valgrind, so there is a pretty noticeable runtime overhead. CFG-Grind slows down programs execution by 85%. I'm saying 85 times, not 85%. And mind it that CFG-Grind is pretty fast compared to other Valgrind plugins. But if we account for everything, time to compile and extract the histograms, then the cost of dynamic and hybrid classification is not much higher. It's 80 times the cost of using the LVM-based static classifier, and it's 4 times the cost of using the x86 static classifier. And, well, in the case of the dynamic classifiers, we don't really need to compile the program, so we could remove that to make the overhead lower. But the fact is that once we account for everything, dynamic classification is 4 to 9 times lower than static classification. The precision of dynamic classification is just a tiny bit better than static classification in a setting without an adversary. But once we throw in an adversary, the precision of the dynamic classifier is much better, about twice as high as the static classifier. A question that we leave open is if it's possible to keep this precision without having the overhead. That's a question for some future work. So that was pretty much what I had to say. Our artifact is publicly available in case you want to try it, and we would appreciate contributions, of course. And to know more about our work, I recommend the paper, which is available in this URL. So thank you very much for your time.